You may be seeing a problem. I guess these instructions are slightly offbeat, but we're given in advance that this third degree polynomial has two distinct rational zeros. Now, you know it could have as many as three distinct, but you're given this. You don't have to figure it out or anything. It's given that you have two distinct rational zeros, more frequently called roots, I think. And let me give this thing a name. Standard one is capital P of x. And what we know is we have two distinct rational roots. And what that would mean here, I'm using A and B, so that would mean that P evaluated at A. Yes, that A's withstood a lot of criticism, and then that's equal to 0, and then this is P evaluated at B. Okay, all equals 0. Now, of course, the power of this, there's two ideas really here, I guess. One of these has to be repeated, okay, in order for you to have a third degree equation. So let's take a look here. I just chose A to be the repeated root, and again, you would have x squared and x, which will give you x cubed right here. That's why one of them necessarily has to be repeated, and without loss of generality, we just made it be A, okay? So this is something called the factor theorem. Any zero corresponds to a factor, okay? Now, you're going, wow, is that really enough information? Well, it turns out it is. Notice when you expand this out, minus a gets squared, so it would be plus a squared, the minus b sticks. And so the constant term in this expansion is minus a squared b. All right, minus a squared b. We don't have to expand the whole thing out. That's the beauty of this particular problem, I think. Something that you might not think of initially. You might just try to use Vietas or something, you know, or do the rational zero theorem, something like that. But what we know is that since minus 7581 over 25 is the constant term in the real live equation, and then this is our kind of our literal constant term here, minus a squared b, we can equate these two things, all right? Now, of course, the minus signs will go away here, but what in the world here? We have two unknowns here. So what do we do right here? Well, one thing you can do is determine the number of divisors, or not the number of divisors, but the prime factorization of 7581. Now, let's just take a look at this fairly quickly here, because I don't want to, most of the work is actually right here. Now, so 7581, notice that the sum of the digits are 21, and that is divisible by 3, so the entire number is divisible by 3. It's a well-known divisibility test. 8 plus 1 is 9, 9 plus 5 is 14, 14 7 is 21, and 21 is divisible by 3, okay? So this is equal to 3 times something. Okay, 3, we know that so far, right? And again, y'all, we're trying to get, we know downstairs is 5 squared, right? We just want to see what this is and see if we can make some associations over here on the right-hand side. All right, now, it's clear that 2 doesn't divide this. I should have said that first. It's clear that 5 doesn't divide this, so let's check 7. Now, there's a pretty cool little, not so common divisibility test for 7. You can multiply the last digit by 2 and subtract it from the remaining digits. If that is divisible by 7, the entire number is divisible by 7. So you have 758 minus 2, folks. And that's just part of this little trick. I proved this in another video. But you take the last digit, multiply it by 2, and you subtract it from what's remaining. Okay, now that would be, what, 756? Now, I don't know if that's divisible by 7, so we can do the same thing again, okay? This would lead to 2 times 6 is 12, and if you take 12 away from 756, you get 744. Now, I did leave that step out. Is that what it is? 12? Yeah, 2 times 6 is 12. Take 12 away from that, and you get 744. Okay? Or no, wait, sorry, y'all. You would get 12. Let me erase that. You end up getting, let's see here. So what you do is you take 2 times 6, which is 12, and subtract it from 75, and that gives you 63. Okay, that gives you 63, and that is equal to 9 times 7. Okay. Okay, now, so we know that 7 appears in the factorization. So you're at a point now where you have to physically divide 3 times 7 into 75. There's a divisibility test for 11 that does not work. Okay, there is one for 13, I think, and I'm not sure about 17. But you're stuck right now dividing 21 into 7581. And when you do that, you'll actually get 2 copies of 19. And y'all, this is where the only real work is done. That is done right here. This is time consuming to determine that the prime factorization of 7581 is 3 times 7 times 19 squared. You would discover that 3 and 7 are prime factors. You would divide the 21 into 7581 unless you know some other divisibility test, and then you would get 19 squared as your quotient, okay? Now, what's so cool about that? Well, what we get right here is that this would equal to 3 times 7 times 19 squared over 5 squared. Okay, folks, but look at what we got going on right here. There's a squared object right here, and the only perfect square on the right-hand side is 19 squared over 5 squared. So in other words, this tells us that a squared has to be, there's absolutely no other possible arrangements here, a squared has to be equal to 19 over 5 squared. Isn't that cool, ladies and gentlemen? A squared has to be 19 over 5 squared. And then what's left right here, b, okay, this would be, this is divided by 25 squared. So b would have to be equal to, let me write this right here, this would be 1, b would have to be 19 over 5, and then we have what's left here, folks. Sorry, this part got taken up, so that means that a would have to be 3 times 7. Okay, everybody agree with that? See, you got an a squared right here, and 19 over 5 quantity squared is a square rational number. All that's left for your b, y'all, sorry, this is b. This is b right here. Okay, my bad. That would be b. B would be 3 times 7. So what we've learned right here, just by inspecting the prime factorization here, is that a has to equal to 19 over 5. And b has to equal to 3 times 7, which is 21. Okay? Y'all, and that does it. So this was an easier cubic in many regards because you didn't have to do the rational zero theorem. You were given some non-standard instructions, which actually made the problem easier. And again, the primary work here was just to know that all you had to do was work with the constant term based on this expansion right here. And then the biggest chunk of computational time is figuring out that 7581 is equal to 3 times 7 times 19 squared. Once you do that and you compare it to the expression or the term a squared b, it all falls into place pretty nicely. Okay, so these are the solutions, folks. The zeros are 19 over 5 and 21. Y'all notice this is a rational number. 21 over 1 is a rational number. This is a real live rational number. The natural numbers are a subset of the rational number. So this doesn't defy anything about the instructions. So the two distinct zeros would be 21 and 19 over 5. Okay, again, if you have a quarrel about this being rational, it's rational because 21 is equal to 21 over 1. Boom. Okay, thanks for viewing.